Can you just set it in with the
Yeah.
Okay.
Excuse light work, right?
I haven't excused it.
No. So you usually are supposed to send me an email before, right? Okay.
That when I come back.
Okay.
Sorry about that.
Yeah. If it's late, it might not be in that package. That's just what I have. But Lucia might still be working on it. Yeah.
So homework 3 should be done in because I'm the same amount of time.
Yeah. Oh, hold on. Let me grab the rest. Double check.
I thought you wrote this on the top. I was pretty sure I did. When I clicked it out,
Oh, the highlights. Okay.
so
No
you just want me to?
Yeah. You can just draw on it.
Okay.
Yeah. And you don't have to turn that in right now. You can turn it in later. Okay, so much paperwork. What am I doing?
Let's wait after class.
What? Okay, how's everyone doing? Bad. Good. Honesty. That's good. Medium. Love that. Good. I saw some bad. Okay. I saw some of you at the open house yesterday. So fun. Had a good time? Yeah. Yeah.
So, is it part of like, oh my God, is it a part of credit to go, or is it extra credit?
Extra credit. I don't think I can require you to go because it's outside of class time. Right? So some people have these things called jobs and responsibilities, and they're not able to go. So they shouldn't get punished for that. Yeah. We were there till we started at 7:15, left at 9. But of course, you can come like right before the sunset. So the gate opens about 30 minutes beforehand. You can see us set up the telescopes. It's kind of boring, but it's pretty and you take photos. Oh, sure. So the nice thing, I guess this will get worse. Is there a day that works better? So we have them Wednesdays and Thursdays. Last one was snow ash out, and we couldn't do it because of the ash. But next one, I believe, is on the not next week, but the week after Thursday. Yeah. Yeah. We tell people not to, so we don't have 50 cars. But if you carpool, that's perfectly fine. Okay, any other questions before we start? Have you found this? This is in the information module. It's the top thing. It has a bunch of words. I strongly suggest you read the words. So this is what you need for, I know reading is not everyone's favorite thing. I couldn't make a TikTok about this because I'm just not that talented. So this is instead of exams, right? So this is what we're gonna base your grade on. And I'm gonna ask you what things I care about. I also want to hear from you what you care about. So even though I put up a lot of questions here, if you answer stuff that I didn't ask, that's perfectly fine. You talk about stuff that I didn't request, that's fine too. I want to know who you are, why you're taking this class, right? Any questions about this? All right. Let's jump in. What's that? A moon? Like your moon? Thanks. Is it Pluto? Ooh, that would be cool, right? So let's see if we can figure out what the fuck we're looking at. Sorry. That's too dark. Wait, is that's what we normally use, right? I don't remember. So it's clearly roundish. That's a good start. There's a lot of cratering. Surface old or new? Old. What else do we see? What are the geologic processes that we see or don't see? You don't see tectonics. So you're looking across and you're looking for things that are like long linear features. Maybe like we've seen compression at Venus, like lots of lines stacked together. Or you don't see like ranges of mountains like we have here on Earth. So there's no clear tectonics. I like that answer. Anything else? So you're talking about impact craters, talking about tectonics. What else is there? No what? Okay, so you're looking across the surface. All right, I don't see any volcanism. Do you? I see some weird stuff. You see any weird stuff? Yeah.
That white crater on the right.
This one?
Yeah.
Yeah, that's weird, right? And that's weird. I haven't seen that before. Okay, what about the last one? Liquid water erosion. Is that evident here? No like rivers, no deltas. So what do we know about this object so far, other than the things that we said? What can we infer about the three types of planetary properties? Size, distance from the sun, and rotation rate. Yeah. Yeah, no erosion. Good.
We got to probably tell that it's smaller because of the lack of tectonics or volcanism.
Right. So if there's no volcanism, there's probably no tectonics. Right? Right. If it's small, there's probably no volcanism and there's probably no tectonics. Right? Because the interior cooled off too quickly. Is that fair? Okay. Distance from the sun, a little hard to gauge here, right? But what object are we looking at? A moon? Okay, I heard Pluto, I've heard a moon. What if I told you this was in the asteroid belt?
Oh, this is the one.
This is Ceres. This is the largest asteroid. And it's round. And these white things here is water ice. It has water underneath the surface, and it basically it's frozen. There's no atmosphere, but when it's exposed to light, it sublimates, it evaporates, and spews onto the surface. Okay, so we understand terrestrial geology, that's geology about rocky bodies, pretty well. We found out that this was small. It is quite small, significantly smaller than those other objects that we saw last time. Do you remember we had all the planets in a line? And then we had this little tiny dot that you could barely see. That's it. I just zoomed it. Okay. I always say, oh shit, this is gonna take forever. I always say that fun stuff happens when I'm teaching this class. So there's currently this really beautiful comet. We're not quite at the point of talking about comets, but I just thought that we should look at these pretty pictures. So this one is from the Andes Mountains. And what you're looking at here is essentially a tiny snowy dirt ball. So we'll talk about these in more detail. We'll even see close-up pictures because we've visited them with spacecraft. And what's being left behind is all of the gas and dust from its surface that's liberated as it gets close to the sun. Not liberated like, you know, but like liberated, like released. Okay. Does that make sense? Okay, so that's a cool picture, but everything's cooler from space. Oh, why was that so many? My God. Sometimes I just want one and I don't get one, and sometimes I get 15 in a row. Okay, let's go back one. There we go. All right, so this is from the International Space Station. And I'm going to tell you what you're seeing, and then we're going to watch the video. That's the comet that we just saw. It looks tilted here because it's being bent. The light's being bent through our atmosphere like a prism. It's like when you look at a straw in water and it like looks bent. You ever seen that before? Okay, I would do that, but this isn't clear. And then I'm going to turn the lights off completely. It's a little bit better to see on that side. This is the top of the atmosphere where particles are hitting it, and they're creating aurora. So we talked about that previously, like the northern lights. So this is something similar that's happening up here. It's just not happening at the poles. Okay. And then that's cool, right? That's pretty. So now let's watch the video, assuming this works. And Twitter is not really fun, but you can rip videos from astronauts. They just post them on Twitter, like from their personal accounts. Pretty sick. So this is astronaut posted this today. And I was like, well, definitely including that. And so this is the comet, and he is flying towards the daylit side. So we're going to watch the sunrise here while he watches the comet rise. And these colors are real, by the way. There's blue in there for reasons that we'll talk about later. This is a really gorgeous comet. It has a very long name, so I'm not going to refer to it by its name. But you should, I think, be able to see it at its peak brightness on the 13th. So that's why I'm bringing it up. Cool.
How are you recording?
Is it?
How's it recording?
So it goes to this phone. Yeah, like literally an iPhone.
Yeah, you said he was flying towards it? Is he like on a plane?
No, he's on the International Space Station.
Oh,
He's an
right.
astronaut. Yeah.
From space.
Yeah. Hold on. That's better. What did we do? I don't remember. I'm gonna have a giant sticker. Okay. Here is the geologic history of Venus. This is where we ended on Tuesday. We're just gonna really quickly wrap up some of the geologic histories of the terrestrial planets. We talked about the fact that there are very few craters observed on Venus's surface. So we think that a majority of it is quite young, probably between 600 and 700 million years old. Likely there's all three types of volcanism present and perhaps active. People argue about this. Like that's what scientists do. They just like write papers, and then other people write papers to like argue with them, and then they go to conferences and one person gives a talk where they say there are volcanoes, and then the next person says that person's wrong. It's really fun. I mean, for nerds. And there are tectonics, lots and lots of them, but not plate tectonics. So we see these examples of like, you know, crust being deformed and compressed into rings, like rings in a tree. And zero evidence of erosion. Recall that the rotation rate of Venus is once per year. So even though it has a very thick atmosphere, there's no wind essentially at the surface. And certainly no water because it's like 700 degrees. There's Mars. That's everyone's favorite massive volcano. What's the right size here? This object? Arizona. Right? So that's big. You stand at the top, you look around, it looks flat. You're 20 kilometers in the air. but you won't be able to tell that you're on the top of a mountain because it's so wide. There is a lot of impacts. There's more in the southern hemisphere than in the northern hemisphere. If you really like Mars geology, I can do that later in the semester, but otherwise it's going to take so long, so I'll just go on and on and on. The largest canyon system in the largest canyon in the solar system exists here. And this is a really cool YouTube video where you can like fly through. They have it modeled in a planetarium. You can like fly through it as a group. And we saw, of course, dunes, and we saw dust devils. There's also glacial features in the northern caps. Yeah.
How much bigger is that canyon to like canyons we have on Earth?
Yeah, so Valles Marineris is about the width of the US. So imagine a canyon system that starts in San Francisco and ends in Maine. Yeah. So of course our largest one's like maybe 2 states, right? Grand Canyon is the biggest one, and I think it's like Arizona, a little bit into Utah. Is that correct? I have to double check. I can't say that loudly. We have time for this. Okay. We talked a little bit about the fact that we put a seismometer on Mars, and we can use seismometers to find Mars quakes. The Earth, we call them earthquakes, but if they're on another planet, they're the quake of that body. And this is what they look like. They look like little pings. So the Insight team put out this very informative video with very annoying music. I promise you. But the only reason we're going to listen to it with the sound on is because they include the sound of the ping. Yeah, I don't know. Okay, so they landed on the surface and they lifted to an right. That's the seismometer. They place it far away and that's around. And so this is just the image that we're going to come back to later. We thought that there was actually that is not only on the fact that we're going to get the data, they'll also go and they'll find and do it after we have and there's the 3 strikes. That? I don't know how to make this louder. Let's see. I do know how to make it louder. Now, why they have the background music going the same time befuddles me. Like, so you hear it burning up in the atmosphere, and they hear it. You want to hear it again? Are we good? One more time. One more time. Okay. That at the very end. Well, that's 3 individual pieces hitting. Okay, so now enough of that sound. Horrifying. And let's just look at the craters. So what they did here is they take images of the surface and they're using an enhanced color here. So they're looking at the difference from previous observations. And this is all new material from that impact flashed in. Wow. Okay. So we can tell a little bit about the interior of the planet from that seismometer. And the bottom line is that, oh my God. The bottom line is that Mars is active, but likely very close to being dead. Okay. Very few Mars quakes. Okay. You saw I already gave away the, let's ask this hypothetical. What would Mars look like today if it were twice as big? Right? Because now we're using a mental model to try and understand hypothetical situations. So would there be more volcanoes, more tectonics, and more craters would there be fewer tectonics? Sorry, I'm not gonna be able to do this. You read it. It's too many letters. Okay. It looks like everyone's in two camps. Anyone else want to click in? Who hasn't? 5, 4, 3, 2, 1. Okay, that was someone just got in right on one. That's impressive. All right, we have two camps. So if you are in camp A or camp D, I want you to convince your nearest neighbor. Just for like a minute. Just find your nearest neighbor, find someone who's not the same as you, and convince them of it. Okay, did you convince your neighbor? Did you talk to your neighbor? Okay. Again? Let's see if it worked. Okay, interesting. That's pretty good. A lot of motion towards one direction. Click in if you haven't. Anyone want to describe what they picked and why? Raise your hand. Someone we haven't heard from today? Yeah.
So, I suppose if it's bigger, and it's not infectious, that is more about things than this resonating.
Okay, interesting. Make more new surface. Wash away the old crater. Interesting, interesting. So which one did you like? Deep. So if you're larger, you have more volcanoes, more tectonics, and because both of those are good at erasing old surface, you have fewer craters. I agree. All right. All right, and of course, that's kind of like what Earth is like, right? So if we look at the Earth, really hard to find good craters. You know, I have to kind of like scour the internet. They're just not abundant. And there's like less than 200 total that you can find. Some of them look like that. Like you put a gun in my head and say, is that a crater? I was like, I don't know, you know?
Doesn't do the erosion, right?
Yeah. So that's in here, you can see those are streams coming in.
Yeah.
And they're feeding it, right? And this is like a little weird ring lake. Because as you punch in, the sides are down, there's the lowest part, and then the ground rebounds. And so you have this weird bulge in the middle. You make this weird ring lake. Definitely volcanism. Lots of volcanism. We like that. Anyone know what that is? No. Mount Fuji, correct. Mount Fuji is an example of a standalone mountain that sits at the edge of the rim of fire. So you get a lot of these on the edge of the rim of fire, whereas Mount Everest is the result of compressional tectonics. And so it's part of a large mountain range, just like the Andes are part of a large mountain range. When you see ranges of mountains, generally speaking, that's a tectonic feature. When you see a lone mountain, probably a volcano at some point in its life. Okay, and then do we have erosion? Yeah, we're good. Active, geologically active? Yeah, for sure, right? Okay. Cool. So let's use all of this information. I'm going to show you a planetary surface. I want you to stare at it for a little while, and then we're going to make some things about it.
What did you say on the top? Please don't.
Okay, so based on what we know about terrestrial planets, we might expect to just have a look at this for a while. Try to think to yourself what processes that we see physically on this surface. And then I'm going to ask you to infer what the body might be. We played this game a little bit before, right?
You altered the image, right?
What?
Did you alter the image or is that?
I said quiet, you know, don't give anything away. Okay. People feel confident that they have their decisions? No, no one does. Okay. Fucking didn't answer about whether this is a trick question. Okay. Do you see impact craters?
Yes.
Okay, what do you think you see? There.
You were asking?
Yeah. What do you think you see?
I like the circles?
Right. So like these in here?
Yeah.
So what's the difference between a volcano and an impact crater? Yeah. One's up, one's down. You can't really tell in this picture. Which of the two tends to be more perfectly circular? Impact craters, right? So there might be a little bit of a problem here because they're very similar shapes. So if you said to me that looks like an impact crater, I'd say it looks a little bit not rounded. But I'm not expecting you to know that. But if you gave me either one of those, that's kind of the feedback I give you. Do you see any like perfectly round circles? No. Yeah.
Doesn't tectonics reshape the crater?
It could, yeah. You're saying like it could tilt it out of the way,
Yeah.
but like there's no lines that are like intersecting it, right? Okay, so let's ask it a second question. Do you see evidence of erosion? Where? What? Maybe rain? Okay, where do you see that? This one is not as good as that one. That's a better screen. Where do you see the evidence of rain? Like this or like this? This here or here? Here? Okay. Yeah, okay. You can see some arguments like there's like some weird texturing here. Maybe this stuff is like flowing down. That's the argument. Okay. What about tectonics? Where? Here? Oh, here. Yeah, that could go, you know, I could see an argument for, is that a crack? Is that erosion? Those are kind of tricky to tell between two, right? Okay. What about volcanoes? Any volcanoes? Where? The dots all scattered around. Yeah. A buckload of volcanoes, right? Okay. All right. So let's put that all together. Okay. So come on now. You give this away, I'm gonna be pissed. There we go. Okay. Many volcanoes, no craters, right? So what do we know about this object? Big. It's big because it's got a lot of volcanoes. Okay, what else? It's got a lot of volcanoes, it probably has thick atmosphere, no? Always outgassing, right? And it's got a young surface for sure, brand new surface. Might be the youngest surface we've seen so far, right? So how big do you think this is, and where do you think this is? Yeah,
What is?
right, Earth? Okay.
You said it's young surface.
Okay, what if I told you I didn't alter the image? Venus, okay, I like that choice. Anything else? Anyone else? Okay. This is Io. Io is smaller than the Earth. Is everything that I said a lie? No. Okay, so we start off with the mental model, okay? And then we are introduced to new data and we're forced to adapt. So this is a body that is smaller than the Earth, and it's one of 4 moons of Jupiter. This one is the closest. This one is second closest, then third and fourth. Okay, we're going to see that in a few seconds. So we have to now talk about how does our idea of geology change if we're talking not about rocks, but about ice. Because each one of these bodies doesn't have a crust made of rock. It has a crust made of ice. Which is easier to melt, by the way? Ice, right? That melts in my drink. Right? If metal melted in my drink, we'd have a bad day. Okay. So this is super volcanically active, but it's small. So this is really messing up the class, right? All right. So here's the questions that we want to ask. Why are Jupiter's Galilean moons, we call them the Galilean moons, but those were the 4 moons that we saw when Galileo used his telescope and he could see that they were orbiting something that wasn't the Earth, right? So as a group, we call them the Galilean moons. There's actually a lot of them. We'll talk about them in a little bit. And in general, we're going to ask the question, why are small icy moons more geologically active than small rocky planets? Okay, and I already kind of gave away the hint there. It's that it's easier to melt ice than it is to melt rock. So you can make new ice surfaces easier than you can make new rock surfaces. And I'll prove that. Okay. Okay. So many moons, so little time. This is really great that you can't see any of that. How do I stop that? Let's see if I can get the thing up there. Go away. Okay. Okay. So they're small moons. These are the really small ones. They're not spherical. Look at the size bar here. When they're really, really small, they don't have enough gravity to pull them into a circle. And so you get some funny shapes, like lumpy potatoes. Okay. Then you have the medium and large moons. So these are all to scale, just so you can compare. There's the moon, and that's Mercury, right? Just for these 2 objects comparison. These are the, you'll see that, for example, Callisto is larger than Mercury. What's that? Ganymede, larger than Mercury, physically larger. Similarly, Titan gets the name because it's huge. We'll talk in detail about these 4. We'll talk a little bit about Titan. We'll talk about Enceladus, which is down here, which is super tiny. And we won't really get to talking about all of them, but there's a lot of bodies. And this is not even close to how many satellites each of these individual objects has. Jupiter has these 4 that are the main, and I think it has something like 60 more that are small and stupid. Okay. That's the Galilean moons as they were drawn in his notebook. I just inverted the colors, obviously. And then this is the Galileo satellite that flew to Jupiter. And then they had a probe that went down into the atmosphere. We'll talk about that when we talk about atmospheres in general. But a lot of the information that we get about the surfaces comes from spacecraft who go very close with a camera that's much worse than your iPhone to take some incredible photos. Okay. Not to scale, obviously. Their relative sizes are to scale to Jupiter, but this is not to scale. Imagine that's like closer to you. And they're also not at the right distance. But this is the right ordering. So first it's Io, the one that looks like a hellscape with no craters on it. Weird yellow color. Europa, like weird brownish stuff. Ganymede, weird. Callisto, dark. Okay. Okay. So these are some surfaces of these bodies. On the left is Io, very strange colors. And then Europa. I look very closely at it. This is in color. Just looks weird. That's Enceladus. In my opinion, one of the most beautiful moons. These are called the tiger stripes. Each one of them is named after a river in the Mesopotamian region. This is Titan. Does that look strange? What does that look like? What? Well, it used to be a river. Or maybe they are still rivers. In fact, they are still rivers, but they're not rivers of water. They're rivers of liquid ethane. Now, if you don't know what ethane is, it's the flammable stuff that, if you think about like butane, that's a different type of chemical ethane. They're similar. They're not exactly the same. Ethane is like the stuff that you drink, get you, anyway. And then Triton. Triton's a weirdo. Okay, so there's these really small bodies. I just showed you all them all compared to the moon, and yet they have all of these features that you would never expect to see on a small body if you believed this model of how size, distance from the sun work into place, right? So now we have to explain this. Okay, so the reasons for this is something called tidal heating. And of course that they're mostly made of ice. So I mentioned that before, and I'm just going to say it again. Ice is easier to heat up. You need less energy to melt it. So one thing that we're going to see when we talk about these bodies is the ones that look old, the ones that sort of fit our expectation. They usually don't have a source of tidal heating. That's an additional source of heating. And maybe their composition is different in one way or the other, right? Also, orbital resonances. We're going to attempt to explain this, but if this one sucks, sorry. You can just tell me. Okay. Let's do orbital resonances first. This diagram, I think, goes on forever, hopefully. So what I want you to do here is I want you to, this is the correct ordering, and this is not the right distance, but timing is correct. So every time Io goes around once, Europa goes around twice. Sorry, did that wrong. Every time Europa goes around once, Io goes around twice. And you can watch that because just watch right up here. Okay, they're all going to line up. Okay, this one and this one, right there, right? And then this one and that one lined up. And then this one and this one lined up. And then this one and this one will line up in now. You see? Okay, so what is this like? This is like you're pushing your cousin on the swing and you don't really like it, okay? So you don't actually care if they have a good time. You just want to see how high they can go. So when do you push them?
Like push them out? Or like...
Yeah. I mean, we've all used swings. Has anyone not used a swing here? Okay, good. So we've all used swings. Okay, common analogy that I can actually use. No one's making fun of my food. Okay, so when you push them to get them to go high. Yeah, so that they're coming back to you. As they get close, you push, right? And you wait for them to get to the very end of their swing, right? If you're standing like, when you're like a little kid and you're trying to get someone started and you can't figure out how it works, you're just arbitrarily pushing them, they don't go very far. So if you give them a push always at the same time, each one of those pushes starts to build up, starts to add. And you get a larger motion than if you had just pushed randomly, where you can average out what's happening. Okay? And in this particular case, if I just have random pulls on this body, that is Io, if I just randomly pull on it with gravity, then nothing really happens, not that special. But if I always pull on it in the same location, that can start to add up. And that can be a significant source of internal heat because I'm literally stretching the planet back and forth. Okay? As I stretch the planet back and forth, I can create a source of heat because just like if you do this, your hands get hot. Now imagine the whole planet is doing this all the way through. Whole thing is flexing and flexing and flexing. Every time it flexes, it puts heat inside of the rocks. It puts heat inside of the ice, right? And it melts it. Okay. Anyone hate that? Oh, good. That wasn't so bad. It changes the shape a little bit, so they become slightly eccentric circles. And that's also really important because as I get closer to an object, gravity pulls on me more. Okay? Let me show you how that works really quickly. Does anyone know people have been to the ocean? Everyone been to the ocean? Okay. Anyone understand how the tides work? The moon? Okay, good. I like that answer. Something about the moon. How many tides are there in a day? High tide, low tide. No? Anyone a surfer? No. No surfers in California? That's shocking. Okay. There are 2 high tides and 2 low tides. In fact, there is a bulge on the side that faces the moon. There's a bulge on the other side, not to skin. Okay. So what's happening here? This one is super easy to explain. Okay. Ground is made of rock. It's being pulled towards the moon, but not as strongly as the water. The water wants to go. That one is everyone's okay with? Mostly? Okay. Yeah. So the rock doesn't want to move. It's being pulled by the moon. But the water is much more flexible, right? Water flows. And so it can be sort of pulled in the direction of the moon. So this bulge is almost the easier one to explain. But why does this one exist? Okay, so I said that gravity acts stronger when you're closer. The center of the planet is actually closer than the far edge. So the center is being pulled towards the moon more than this bulge is. And this is essentially left behind. So the Earth is falling away underneath that water. And so if you're standing on the Earth, it looks like the water is moving away from you, but really you're moving away from the water. That make sense? Okay, yeah.
Since it's like that, there's 2 different, so there's 2 high tides and 2 low tides. Are there also 2 versions of those? So one high tide bigger than the other high tide, and vice versa for low tide?
So they vary throughout the entire planet. You'll get like less strong tides, for example, at the equator than you will at there's these wonderful pictures of like docks in some places near the pole where the water level can rise like 20 or 30 feet. And so your dock literally one day it's your boat with the water on it and then it's on the ground. It's rises up and then it's on the ground. And so the strength of the tide can be quite complicated based on how shallow the the ground underneath the water is, right? So you're gonna notice a tide less when you're out in the middle of the ocean than you will if it's a very, shallow but deep, like long beach. Whereas if it's a sharp beach, that small difference, you're not gonna notice as much. But if it's long, you're gonna watch the waters go all the way out and then all the way back, right? So tides are much more complicated, but I'm trying to simplify them.
So it's only the beach, right?
It happens in the ocean, but you won't notice it as well. It's also you're standing on it, right?
Yeah.
Okay. Okay, so this is how tides work. And now I want you to, oops, hold on. Yeah. So now I want you to imagine what happens if a planet, for example, is going around an object and changing how close, how far it gets to that object. Okay. Oh, the moon has a bulge too, but we don't care about that. All right. Why is this not working? There. Okay. The moon is currently on a near circular orbit. If it was in a more elliptical orbit, remember that's like a squished circle, right? The moon would experience, so it's going to get closer to us and farther. This is us, blue dot. This is moon, white dot. Okay. Is it going to experience a greater, smaller, or the same range in tidal forces? I just opened it up right now, so if you didn't do that before. It won't matter for this selection. Okay, okay. Dial in if you haven't already. 5, 4, 3, 2, 1. Okay, interesting. It's about 3 to 1. Anyone want to defend their answer? Do you think you're in the right camp? And we haven't heard from today? And back row. Yeah. Smaller because it's got more distance to cover. Okay, so let's think about this question together. As you move from here to here, what are we talking about with the tidal forces? Yeah, is the range going to be greater or smaller, right? So we're comparing this to a circle, right? It's circular. I'm not getting any closer. I'm not getting any farther. You have a question? Or are you going to clarify?
So it's not so it's moving further, right? So
Yeah, so here it starts out far, it's gonna get close, and then it's actually even gonna get farther than it is here. Yeah.
Maybe smaller and it's like, orbiting on the left side, and when it gets closer, it would be greater length and the gravitation will go over the moon.
Right, okay, so as you're farther away, the pull is weaker. And then as you get closer, the pull is stronger, right? So if we're just talking range, not the total amount, right? Because obviously if you're close and you're in, yes, the total amount might be different if you get a big pull versus a small pull and trying to average those, right? So here, because I get so close, now I get a big pull, so it's a large number, and then I go very far away, small number. So the range is greater, right? Cool. Does that make sense to folks? Okay.
Would that be dangerous?
Would that be dangerous? Well, look at Io.
Right, like.
Yeah, look at Io. Io has no craters on its surface. It's constantly erupting. And we're gonna see some cool pictures of Io. You're gonna be like, I wouldn't want to live there. Let's look at that. This is exactly what's happening here. So Io has an orbital resonance. That's the one that I showed you before. It's getting kicked by its neighbor moons. And it's made of ice, so it's really easy to deform. And it's got an elliptical orbit. It's got all of the worst possible conditions for just getting its stuff kicked out of it. Okay, so here's what it does, is as it gets close, it gets these large tidal bulges, right? Hold strongly. And then it heads away, and those become small. But it still needs to relax. And so as it relaxes, the exterior and interior are compressing like this, back and forth, right? This is the tidal heating. There are some examples that we'll see in the outer solar system where it's not so clear like this, and they will not be as volcanically active. So if you have a small body and you don't have a lot of tidal heating, you would not expect this level of volcanism. This is kind of like best case scenario if you want to make a tiny thing erupt, right? You have all of the things you need. You have something made of ice, you have an elliptical orbit, and you have resonances. Because you might only get one or two of those total, right? Okay. So that's hold on. That's a real picture. That's from Hubble Space Telescope. Io is 2,000 miles across. I have driven Io, right? What's 2,000 miles? Like the US, a little bit less, 600 miles less. So, I drove from DC to here, start this job. I drove farther than Io, right? It's not big. And yet its surface is covered with volcanoes. And this, of course, the thing behind it is Jupiter. Jupiter is massive, right? And Jupiter has, interestingly enough, tons of storms. No surface. We're not going to talk about it when we talk about geology because there's no such thing as geology on Jupiter. Yeah.
I was gonna say, because it's caused by its proximity and lack of proximity to Jupiter, does that mean it's geologically active for a lot longer because it's an extra outside force that's forcing it to be hot?
Yeah, I mean, so one thing that's really interesting about Io is we think it's been active since it formed. Probably formed about 4.5 billion years ago. Is that helpful? Yeah. Cool. And that's the shadow. That's not a different moon. Okay. So here it is, close up. It's about what? Good one. I learned that one. This is about the same size as our moon. And the colors you see are real. Every color there is real. It's a real image. And the reason that it looks so bad is, and what is in eruption that makes it so weird looking? Anyone know? Gases? Anyone know which gases make it look gross? Sulfur. Yeah, what color is sulfur? Yellow. Yeah. So if you've ever seen like Yellowstone, right? We call it that for a reason. The stones there, the lakes there, the geysers have an abundance of sulfur because sulfur is really, really abundant underneath the surface. Okay? So all this weird yellow coloring, it's all sulfur in various forms mixing in. Because this would be a volcano that explodes and then just dumps the interior stuff in here. It all freezes, but okay. You want to see a picture of the volcano? Okay. Do you see that right there? That is a volcano. That is a volcano on an icy moon. And when I say volcano, I actually mean volcano here. We'll have examples of cryovolcanism when it's liquid, like water. This is actual, magma and whatnot. And this is a big plume. Let's see if I can do the math here. So this would be 2,000 across. So that's like probably 500 kilometers. It's a substantial plume. And there's nothing blocking it, right? There's no atmosphere. This is seeing it from above, by the way. So as the thing rotated towards us, we could take a picture of it above. So this is the main plume, and then it's just like spewing out like a fountain. Kind of pretty. Okay. Surface ice vaporizes and jets away. And we'll see an example of that when we look at Saturn's rings. One of Saturn's rings is caused by something very similar to this. We can see the evidence of where this material goes on Jupiter. I hope that's in these slides. Yeah.
What's the temperature like?
Well, that's really tricky, right? So if you don't have, and we're going to talk about this in a couple seconds. Temperature is something that we are very used to because we are in this nice fluid, very breathable fluid that keeps us roughly a nice temperature that we can think about. But if you went to a place like Mars where there's a very thin atmosphere, thinking about temperatures in the same way gets a little tricky because you wouldn't really feel it the same way, right? The atmosphere would feel a lot colder to you. And as you move into the outer solar system, it gets even colder and atmospheres get even smaller, right? Okay, so actually we have a question here about atmospheres. Okay, does Io have an atmosphere? And does A, Io's atmosphere, there is no atmosphere because there's no source of gas. B, there's some atmosphere, but it loses most of the gas it produces. C, there's a dense atmosphere because of all the volcanoes. Okay, click in if you got it. Oh, this is perfect. 2 camps. All right, click in if you haven't. Okay. I got very few people with this one. Sorry if I got you. It's not this one. There is a source of gas, and that is the volcanoes. Okay, so now generally you disagree with one another as to whether or not it loses the gas or it has a dense atmosphere. So if someone next to you has a different answer, you're going to convince them of your answer.
Yeah, so, but we're crossing out favorite, right?
Okay, let's click back in. Click back in. Got it? Yeah, I didn't get anyone on A this time. Good. A few people changed their mind. Oh, someone put A just for the funds. All right, I get it. All right. So still slightly in two camps. That's interesting. How big was Io? What we compared to? The moon, right? So it's very small, but it has been volcanic for like 4.5 billion years, right? Very interesting. Very interesting. Everyone who wanted to click in has clicked in? Okay. All right. The correct answer is that Io does not have an atmosphere. It's too small to hold on to it, even though it's trying its best. It's been outgassing from volcanoes for 4.5 billion years, but that material immediately is stolen. All its hard work. What? No, it's this one. Yeah. Yeah.
The gas that goes into the interior, but the computer also takes some.
Hold on. Let's walk that back for a second. The gases leave the interior in the form of outgassing. They fall back down on the surface, right? But they fall back down because they're contributing to that color. The ices leave entirely. The heavier stuff follows. Right? So we saw that plume, but it never becomes an atmosphere. An atmosphere is like something that's a fluid, right? Something that you can walk around in. Okay. The material that would contribute to the atmosphere, in fact, gets removed and added to Jupiter. And we can see that it gets added to Jupiter. Come on now.
Jay, it doesn't have no crust, right? There's a crust.
There's a crust, yeah. Well, Jupiter doesn't have a surface. Is that what you're saying? Yeah. Jupiter does not have a surface. Io does. Okay, so what are you seeing here? Okay, so this I told you a little bit about aurora. These are places where particles from the sun slam into the top of an atmosphere. So from space, they look like these really cool rings, right? The Jupiter has this big old magnetic field, and it's grabbing particles from the sun, and it's directing them to its North Pole. So you're seeing the North Pole of Mars, of Jupiter. Okay. But what is that? That is Io. Io is magnetically connected to Jupiter. So all the material that comes out in volcanoes gets charged, travels up those magnetic field lines, and smashes into the top of Jupiter. And so this is the place that they're smashing in. And this is sort of like where it's been. So you can watch Io orbit just based on where the material is being stripped off of what it would try to have an atmosphere. That make sense? Anything else you see here? Keen eye. Which one here? Oh, no. That'll be lower. We'll see that later. What? Yeah, that would be really cool if it was. But that's down. We have beautiful pictures of the storm. You'll love them. Different dot though.
It looks like a retrograde motion.
Well, this is not motion on the sky, right? This is just watching it go around. And we see Io here. You see anything else? Yeah. These two? Oh, interesting. What if I told you those were its other moons? Yeah. So in fact, all three of the moons here are connected. We can watch them deposit material. If anything leaves the surface, it just is immediately deposited onto Jupiter. Yeah.
What about this though?
It's probably in this picture somewhere. I just don't know where it is. This is from a press release. My friend John Clark, he works at Boston. This was, I guess, from earlier. He works at Boston now. Anyway. Okay, and that's what an aurora looks like on Earth, just because you can't not have the Earth version. Okay. This is real. This is in real time. Okay. And this is 100% real. Okay. So it looks like dancing. This is like particles that are coming down on magnetic field lines, just smashing into the atmosphere. It's green because of nitrogen in the Earth's atmosphere. N2, which we're breathing in, is mostly nitrogen, a little bit of oxygen, and a tiny, tiny fraction of CO2. This TikTok video is from last year, so, but I did go to Iceland in March trying to see this. It sucked. It's really cool. I only got to see it from very far away. So I went in March, that idea. You should go in the fall when everyone else goes. You go in March, like avoid tourists, you find out why tourists aren't there. So basically you look out at night and you're like, that's weird. Why are these lights in that direction? There's no city in that direction. And I see the moon over there. So like, why is that illuminated? And then you figure out that's north. Oh, fuck, that's the northern lights. Because literally there's this weird blue glow all over it. And you're like, whoa, that is crazy. And then you go and you walk underneath it and you look up. You're like, that's strange. I didn't get this good a photo, but anyway, go see them if you can. Okay. That is Io. Let's talk about Europa. Europa actually, believe it or not, is cooler. Hard to believe, right? What do you think about that surface? A lot of tectonics. Good. Okay. What else do you see?
Scratches.
Yeah, scratches all over the surface. So maybe there's like a giant cat playing with Europa. Yeah, there's a big old impact crater. Okay, so that's different from Io for sure. Just the one that you can see, right? And like this even kind of looks like the moon one, right? Because remember on moon there was one that like threw stuff all around. Yeah.
Is that a crater too? Yeah.
Yeah, over here, this one could arguably be a crater, right? Oh, I guess it's better to see there maybe. Yeah, that could be like maybe a deformed crater. We had that argument about whether that's a volcano, right? You might win that argument against me. It's not, but you might win the argument. Yeah. Okay. You see an atmosphere here?
The color of it.
Like here on the edge? Okay, interesting. Okay. Do you see erosion? I'm only asking what you see. We have to infer things after we see them. Yeah.
It has frozen over, has it, like cracks and stuff on it, and ice that broke.
They look like ice that broke. Like here? Oh, interesting. And ice is kind of blue, right? Huh, interesting. All right, let's zoom in. Let's go look at that spot. Okay. Yeah, lots of fractures, lots of scratches on the surface, right? Very few craters. And the places where there is an impact crater, very bright. Okay. Come on now. Let's zoom in some more. Let's go over here. Okay. This is false color. That's not the same color anymore. High resolution, you have to sacrifice something. So you mentioned that it looks icy, right? Let's look very carefully here. There's these like little, I don't know how you call them, like little squares and pieces. What? Scaly? Yeah, scaly. I like that word. That's better than what I was trying to go for, which wasn't effective. So it looks like little tiny scales, maybe fish scales that are all bumping up against each other. And then these long lines, really weird long lines, and some of them intersect, right? These ones intersect. This one probably happened after that one, maybe something like that, right? We'll explain those in a second. Let's zoom in here and see if we have an Earth analog. Okay, that's the scaly region, right? And it looks like there's these big chunks, and inside that same pattern still persists, sometimes across different scales, right? So this seems to have cracked. And this is the example that you might see on Earth. On Earth, not on Europa, on Earth. So these are ice flows. This is when ice sits on top of water. And do you see on the edge here? They grind up against each other. And so some of the ice gets deposited in the water and some of it gets deposited on the edge. But they form these kind of like weird shapes all over, right? What?
It's like tiles.
Kind of like tiles, yeah, kind of like scales like we were talking about, right? So this is probably what we're seeing in those large scaled features on Europa, like an iceberg field. And if you look closely here, you'll notice that some of them are up and some of them are down, right? So like there's literal shadows in here. And those shadows are from, say, an ice flow cracking and sitting like an iceberg on top of frozen other ice. So ice, a lot of ice, okay? I get tired of saying that. Let's zoom a little bit more. Let's look at this other region here. And what do these things look like? Tectonic features, right? Yeah, they look like cracks in the surface. And that's probably similar to what they are. Here on the left is Europa. And here's the ice analog on the Earth. This is like a giant crack in the ice sheet. And what happens is that it starts to fill in below with water that then freezes because the air is freezing. And so you start to fill that thing back in, right? So this thing here cracked open at some point and was filled in with new liquid, right? The reason I love Europa is because it probably has a global subsurface ocean. The entire thing has this, right? If you zoom in here, probably has something like this, which is a frozen surface ice. And people are more and more leaning towards this one here, which is a liquid ocean underneath the ice. So if you want to look for signs of life, it's actually probably here. This was supposed to be 2022. It's actually launching in 2 weeks. So that should be very fun. October 10th. So I forgot to update that. Who has more water, us or Europa? You say us, right? Like obviously, we're the coolest planet there is. Wrong. That's a lot of water. Another reason why if aliens visited, they would not come here. Okay, there is water on Europa and there's more. Easier to get to. Okay, one final thing, and then we're gonna talk about some other planets. Here's Europa. Let's zoom in this region. There we go. Right? No, it's a joke. That's a joke. That's a joke. Don't believe the hype. But it looks a little. I added those afterwards. It looked like it's like an interchange. It kind of looks like a highway, though. Tell me that's wrong, right? Doesn't that look like a highway? Like one's an overpass. Okay, yeah. I know. Well, I can in post. I'll add it. Okay, let's ask another question really quickly here. What? It looks like a freeway, right? It's crazy. No, but it's not a freeway. I think. I mean, I don't see any cars.
You have the small street too. The country is really small. This is from space.
This is from space, but it's a really big freeway.
They're very small people.
Very small people. So the interesting thing, I'm going to go on a tangent here because I might as well. What we think there probably is at Europa would be like subsurface life. On the surface, there's no atmosphere. And it's freezing cold. So you would die. You and I would die instantly. Microbes die probably instantly. But under the water, there's an available source of heat. There's water. So if you have like a fish that grew up in that region, it might love it. Right? Okay. So let me ask one more question and then we can go. All right. Europa has only ice tectonics, while Io has many volcanoes. Tidal heating on Europa is weaker than on Io, mainly because A, Europa is smaller than Io. B, Europa is farther from Jupiter. C, Europa is not in an orbital resonance. D, tidal heating is not important if liquid water is present. E, none of the above, tidal heating is greater on Europa. Click in. No one clicked in, or it's just not working? Oh God, why would it do this to me now? Okay, hold on. Let me try it again. Does it work now?
Yeah.
All right, it's freaking out. Okay, wait. Before you leave, let me ask. Oh, there it is. There we go. All right, now you can answer. And then I'm going to ask one final question about where we want the class to go. Interesting. Okay, so for Tuesday's class, you're going to turn in your check-ins. That's going to be a packet. It's going to be ideally clipped in some way. You can put it in a folder. That's fine too. But please don't staple it all because I want to look through it. And then I'm going to give you feedback. Yeah.
Yeah, because I don't see anything on that.
Go to information. For the module that says information, it's the top thing. Can everyone see it on Canvas? Okay. All right, I'm going to remember that we need to talk about this answer. We're going to come back to it, but let me ask you one more question. On Tuesday, we have a choice. Do you want to keep learning about icy bodies and talk about Pluto? Or would you like to talk about atmospheres and weather and then talk about giant planets and then get to Pluto later? And the reason why you might want to talk about atmospheres, because like we live in one, and like, why do hurricanes form? Why is there climate change? So we would ask those types of questions. So let's go back here. Dial in if you have a preference for this one versus that one, because I can just change the class to wherever you want. And if you don't care, that's fine too. Yeah, let's talk about Pluto. All right. We can do 2 classes. We can do like 10 classes on Pluto. It's sick. That's literally 50-50. Yeah, that's pretty damn close. Yeah. Someone voted for I, so.
Speaking of this, if you're reading dynamics or icy bodies or.
We'll do ice. What's that? How much put that here and then the group stuff put that here?
Turn in the packet that we were doing on Tuesday.
Next week.
The packet we were doing last class. The.
Tutorial thing?
But this one,
Home for will be over here. Oh, yeah, this is returning home.
And I know I turned it in. And I took
Can you send me a?
I can check. I just turned it in.
Looking.
I don't even gonna.
Be confident.
what's the events right now?
Do you have a question or no?
I'll just look at your. It's like a dog.
Yeah, no worries.